All right, this is lecture 47 on simultaneity. I don't know if I've spelled the word right, but I do know what the concept means. And so that's where we'll begin, is describing what does it mean for two events to be simultaneous, okay? And essentially this is what it means. Give me a second here. I forgot to open my notes up. There we go. If we are an observer, okay, and let us say that there are two events that take place. I'll call this event A and event B. Now I'm not aware of these events yet, right? Because it takes time, right? So a good example of what this event could be is a lightning strike. Okay? So lightning strikes the point A and the point B. Now I'm referring to it as a point, sometimes calling it an event, right? What I mean, though, is the lightning strikes this distance here. Let's say that this distance is L, and that this distance is L. Okay? So this lightning strikes, what I'm going to say is the same time. Okay? Let's assume that there's some bizarre weather anomaly in which lightning is going to strike two places at exactly the same time. Okay? And I'm aware of it, and so I position myself right here, halfway in between the 2 points where the lightning's going to strike, and I wait for it to happen, okay? So when it actually happens, am I aware of it immediately?
No.
No, I'm not, right? Because when I see things, when I observe things, I have to see them. And the way that I see things is I see the light that comes from them, okay? So lightning making light, the word light is in lightning, so we can kind of see that that is some kind of light. It's going to take some time for the light to travel from here to here, correct? How long is it going? What do we know about this? Well, we know the distance is L, and we know the speed of light is c, okay? And we'll kind of relax the speed of light is 1 business for now, and we'll just say write c for the speed of light. Normally if we said it was 1, we'd just write 1. So c times some delta t, right, is equal to L, this distance, yes?
Yeah.
And so, really what I know how far I am from the spot where the lightning is supposed to hit at some time, right? But this is what I need to know. Delta t, how long does it take for the lightning to get to me? Well, it's L divided by c. And over here, it's the same thing, right? This is delta t equals L divided by c. That's the reason I stood midways. Because if these two events do happen simultaneously, then me being equidistant from both of these points, right, I should see it at the same time. That's going to have really good peripheral vision, so I can see, 90 degrees from my field of vision. Then I should see these two things happen at exactly the same time, correct?
Yes.
That's what it means to be simultaneous. If you send a signal from 2 points that are equidistant from each other, on opposite sides of you, then they should arrive at you at the same time. That's what it means to be simultaneous, okay? Let me just draw a picture of what this might look like in a space-time diagram. Here's my t-axis, here's my x-axis, okay? Let's say that, let's calibrate this such that t equals 0 corresponds to the point in time in which I see these two signals come in simultaneously, okay?
Okay.
Well, then all I have to do, that means that this is the point where I see those two signals come in. All right, all I have to do, since they're light, is I can kind of backtrace by drawing, remember the slope of this dotted line, or dashed line, is 1. Because now I'm letting c be 1 again, right? So c is, delta t is just equal to L, okay? So the speed of light is 1. That means that when I draw light on this space-time diagram, I should draw it at a 45-degree angle to the x-axis or to the t-axis. Well, it's both, right? So that means that this event A occurred at some point in the past, and I'm saying it's simultaneous. Now, what do I mean by that? I mean that this line x here, right, this is another way of describing this line, the x-axis, is to say that t is equal to 0. Okay? Because all along this line, t is equal to 0. I'm going to assume, I'm getting a little ahead of myself here, but I'm going to assume that we synchronize all the clocks laid out on our ruler. Okay? We'll talk more about the synchronization procedure later, but it's related to what I'm doing right now. Okay? But let's assume that all the clocks are synchronized. If that's the case, then this entire line is what we call a line of simultaneity. Okay?
Okay.
And for the stationary, or your rest frame, right, for that rest frame, the one in which we're talking about presently, which is drawn as a regular Cartesian coordinate system with the axes at 90 degrees to each other, right?
Yeah.
A line of simultaneity, all lines of simultaneity are written as horizontal lines, Okay, and so for these two events to be simultaneous means that, I'm going to have to fix my dot, there it is, that these two events occurred, and in this case it's some negative number, right? I'm just going to call it negative delta t, sometime in the past, right?
Yeah.
I could have drawn it, I could have said they occur at t equals 0, right? And then I'd put both of these points on this line, okay?
Okay.
So, I know this sounds rather simple, right? But you're going to see that things get a little bit funny in just a minute. But everyone understands what I've done up to this point. I'm describing two events as simultaneous. Right? I could make three events and I could use a very similar reasoning, okay? But two events are simultaneous, right? If I am equidistant from them, okay? Another way to say it is that in a space-time diagram, they occur along a line of simultaneity, okay? And so, for this observer, the rest frame, as we'll call it, is the lines of simultaneity are always horizontal lines, okay? If two events are going to happen at, say, t equals 9 seconds, right? Let's say that 9 seconds is right here, that little tick mark that I drew.
Yeah.
That means that those events occur somewhere in space, right? The position that they occur in space, I haven't said anything about, but they will occur at some point in space, if they are simultaneous, along these lines, okay? So maybe one event here, right? I would observe those two events to be simultaneous. This distance is the same, and they would then occur along this line of simultaneity, okay?
All right.
Okay, again. Now I want to describe a system in which we have two reference frames. One is in motion uniformly to the other, okay? And we'll use our default train and platform frames. I've drawn 4 moments in time here. Initially, our observers on the platform and the train are right across from each other. We synchronize our clocks at t equals 0, right?
Yes.
Some time, and two events occur, right? At A and B, okay? These 2 points that are equidistant from my observer on the platform. So we know these events at some point later, actually it's this point here, right? This observer on the platform is going to detect these two events, okay? And he's going to conclude that these events occurred simultaneously. Because the distance where the event occurred, the lightning strike if you want, will be equidistant away from it, okay? Do we all understand that? Okay. Just like what we were talking about before. The train is moving with a velocity v. At this t equals 0, the train and the guy on the platform synchronize their watches, set them to 0. Some time goes by. Now, the signal from B, I guess I should have labeled these points A and B again and again. Because the guy on the train is moving with a velocity towards the place where B occurred, he's going to see event B happen earlier than the stationary guy on the platform because he's rushing towards it, you see?
Yeah.
The train observes event B first. A short time later, the person on the platform will detect both events. That's when the light signal from A and B arrive at the center point where the guy on the platform stands. He says, A and B occurred simultaneously. And then a short time later still, the light that came from A finally catches up to, or finally arrives at the location of the guy on the train, okay? Because it has to travel a longer distance to reach him, because the distance is increasing with time, you see?
Yes.
The light from B arrives sooner because he's closing the distance, he's closing the gap, so it has to travel less distance to reach him. So it's going to arrive first, you see?
Yeah.
So the conclusion here is that observers in different reference frames will not agree about the simultaneity of events. And let's draw the space-time diagram for that. Here's our x-axis, here's our t-axis. Let me go ahead and draw in our t-prime axis. That's the whirl line of the train, or the observer on the train. If these light signals are going to arrive at the origin, right,
Yeah.
and appear simultaneous, they must be equidistant from the origin. Remember, the whirl line for the origin, right, is just this line t. Right? As time goes on, the guy standing on the platform, his position is higher and higher and higher, right?
Yeah.
So let's send the light signals out. There's my 45-degree light line. Call this A, call this B. This is the point in time, right, which we can now label as, well, we don't need to label, we'll call it t sub AB. This moment in time here is t sub AB. That's when the guy on the platform observes these two things simultaneously, okay? Now, you can already see, where does this event, what time is this at, right? This time here is t equals 0, so we'll write that in, t equals 0. This is the time when the guy on the train sees the light signal from B. This is when he observes event B. Where is that on this plot? Does anyone know? Does anyone see it?
No.
Well, you see where the guy on the platform saw both events occur simultaneously, right here, right?
Yes.
Here's the world line of the guy on the train. As time goes on, he's moving in this direction. What is happening right here? You see that? This is where the light line from B crosses the world line for the train. Do you see that?
Yes.
This is the point, we'll label this t sub B, but we'll call it t prime sub B. And we'll label that time right here, t prime sub B. This is the point when t prime observes event B. So we seem to only be missing one time. That's this, when does he observe event A? Okay? Well, we have to let the light continue traveling, right? It started at A, it went at a 45-degree angle. This is the speed of light. And so we just have to let it keep going. That's a very non-straight 45-degree line. And we'll call it right here. You see it?
Yes.
We'll call that t sub prime A. That's when he observes event A. And we'll put that right here. So, the order of events, according to the observer on the platform, is that A and B occurred simultaneously. Why does he believe that? Because as he was standing here at time t sub AB, he saw light flashes. Hit him in the eyeballs. Okay?
Okay.
Hey, lightning struck. You see? Whereas, before this even happened, the guy on the train, who used to be directly across from him, observes the event B happen. So that's to the left, so he sees a lightning flash. A short time later, the guy at the origin on the platform says, hey, I saw two lightning flashes. The guy on the train has only seen one so far. It was the one from the, to his left. At time t sub A prime, he finally sees the light flash that came from the right. But he disagrees about simultaneity. He says these two events did not occur at the same time. First B occurred, and then A happened. Did I get that right? Yes. First B occurred, then A happened.
So it's because it's taken a little while for the light to reach his eye.
That's right. And it took less time for the light from B to reach his eye because he's traveling towards it. Light has to travel a less distance. You see?
Yes.
Okay. But on the diagram, that's how we can read this. So the way that we can figure this out, what's going on, whether events are simultaneous or not, is by drawing them on the space-time diagram. Okay? And that's what we've done here. And these light lines are always at 45 degrees. This is at minus 45 degrees because it's going backward. It's going from the right to the left, right? This is going from the left to the right, so it's positive 45. Do you see that?
Yes.
Positive 45, negative 45. Later we'll just in general write light cones, right, where the center point is always your origin. Okay? This is the positive 45 degree axis going forward in time. This is going back in time. This is the negative 45 degree line going forward in time, back in time. This is your present, that little point right there. Okay? Okay, pretty straightforward. You can see from the diagram, right, that the moving observer sees event B occur first, and then he sees event A occur, whereas the platform, or the stationary observer, sees both events A and B occur at the same time.
Yeah.
And that's how we can draw it and visualize it, and we can figure out very complicated situations just by drawing these diagrams like this. Okay?
Okay.
The next step is for us to put an x prime axis in. We have the x-axis, we have the t-axis, we have the t prime axis, but we don't yet have the x prime axis to go along with this moving observer, so we can measure distances on this train as it's rolling along. And so that's what we'll do in the next lesson. Lecture, I think I'm alternating between lecture and lesson, I don't know, but it means all the same thing in the end, I suppose. Yeah, so I think what we'll probably do is we'll show it two ways, and we'll spend some time on this, because it'll help in understanding things, I think. And we're not going to do any really sophisticated relativity problems anyways, so we'll spend the time getting to know the coordinate system. It'll make the Lorentz transformations, which are the replacement for the Galilean transformations, I think much easier if we spend some time getting to know the axes. So we'll do a geometrical proof Right? That's how Euclid would have shown it, if he knew about it. And then we'll do an algebraic proof, where we use our knowledge of the equation of lines, things like point-slope form and the formula for the slope of a line to figure out these axes. Okay?
Okay.
All right.